The I2C interface, or Integrated Circuit Protocol, is a little bit more complicated, but it's also very, very common because it is very low wire count and it's pretty simple to implement. It's originally developed by Philips Semiconductor, which has changed hands many times and is now NXP. It's a real standard, so anything that speaks I2C is going to speak the same I2C, which makes it a lot easier to understand than SPI. And there's often another layer protocol built on top of how you read and write to the specific device. So that's where most datasheets focus on rather than the I2C low-level interface itself. It only uses two bus lines. It's the SDA and SCL, and it, again, has a master-slave model. The master is the one that initiates communication, and the slave devices respond to those communications. The advantages of I2C or I2C is that it only uses two bus lines and you can have multiple masters, so it gets a little wonky, and it's very widely supported. The disadvantages are that it's typically slower than SPI. The medium speed implementation is only the medium speed implementation is only supported up to 100 kilohertz or kilobits per second. So it's a little slower. Every slave device must have a unique address, and there's only 112 addresses available. And sometimes those addresses are hardwired, so it's sometimes very challenging to have a bunch of devices on separate sometimes you might have a device that has the same hardware address, even though it's made by a different manufacturer, as something else that's on your bus. Plus, if you have multiple devices of the same type, maybe you're reading a bunch of the same type of sensor in a bunch of different places, you have to figure out how to change those addresses. And they sell other devices that allow you to basically change the address. It's a middleman device that changes the address response of a particular device from one address, its hardwired address, to a custom address that you can make. And that just increases your part count and complexity. So that's the downside. The data transfer size is fixed, so we can only send 1 byte at a time, and it's only half duplex, so you're either sending or receiving. You can't do both, and that's why we have only two bus lines. The I2C protocol itself uses what's called an open drain output. So in this case, you see we have our external pin, and it's an open drain output pin. And basically that means when we're reading from it, it's floating at whatever value. So we would be driving it with either a high or a low. And similarly on the inside, when it's not driven, it's floating. So rather than being high or low, it's at like half a volt or something like that. So if we drive it high, we connect to ground, and that reads as an external device as 0 volts. When we drive it low, it's floating at around half a volt, and that allows the external device to pull it high, which gives us a standard normal high voltage, and this is what we do. So if you look back at the diagram, each of the clock and data lines have a pull-up resistor that keeps the system high normally. So it's a normally high, and we pull it low to acknowledge that something is on the other side, right? So what this does is it allows any device that's on the bus to pull the line low when it needs to, and initiate communication. And we share both the clock and data lines with everybody. So in this case, the pull-up resistor is pulling everything high, and none of the devices want to talk, so it's idle when it's high, and it stays high. When somebody wants to talk, they pull the clock line low to 0, to ground, as you can see down here. So this guy wants to talk, that pulls the bus line low, and now the master can say, oh, somebody is ready to communicate, right? And it could just be the master too. So This is what the I2C or I2C configuration looks like. We have a microcontroller, which is the master, and then we have a bunch of slave devices, and sometimes another microcontroller could be a slave. And you'll see there's the pull-up resistors here that pull both the data lines and clock lines high. To make that the idle state. And what's not shown is the common ground. All of these have to have a common ground. So you still have 4 wires. The SPI interface actually has 6 because you have to have a common ground and you have to have VDD to those devices as well. But those are typically ignored because they're assumed. You always need a common ground. Right. So in this case, we actually only need, besides the pull-up resistors, as long as somebody is pulling them high, as long as we have a common ground, you really only need these 2 wires. So we don't count power and ground in the wire count typically. Right. So the I2C bus control consists of first a start bit. So we have a special signal where SCL, the clock line, is held high or in the idle state, and if the SDA is sitting high for a certain amount of time, we consider that idle, right? When SCL stays high and we have a falling edge on the SDA bit, that's what we call a start bit. So the very first falling edge is our start signal, and then we hold that low for a time, and then we can bring the SCL low, and then we can start transmitting data. And notice here that the low doesn't really mean anything. We just hold it low for a certain amount of time. The first rising edge is where we will latch in the first bit of data. So for here, once we have our initial start bit, when SCL is rising, that's when we're going to read in a bit. So we start off here, we set up the next bit on the falling edge of the clock, we latch in on the rising edge of the clock. In this case, it would be a 0, set up the next bit on the falling edge of the clock, latch in on the next rising edge of the clock. In this case, it'll be a 1, set up, sample, another 0, set up, sample, another 0. And that's how we transmit data in I2C. And this all follows a start bit. Then if after the 8th data bit, our frame sizes are always 8 bits. After the 8th data bit, the master lets the clock line, lets the data line go high, it goes idle, and if the receiver, if the slave is there or responds, it will pull it low, and that's an acknowledge, right? And that's what we see here. If they leave it idle, that means either the device didn't hear it or it wasn't performing. It's the whoever is receiving the data, which may be the slave or the master, because it's bidirectional, has not responded. So it's a non-acknowledge, right? So if it stays idle, something has gone wrong, or it's the end of the it's the end of the transaction, right? So what we consider as one transaction is we have a start bit, which is always initiated by the master. Then the master drives the clock, and either the master or the slave will drive the data on the thing, and whoever is receiving, whichever the role is, will ACK or NACK the device. And then we go to a stop bit, which is where both of the lines return to high, basically in an inverted. First the SCL line goes high, goes idle, then SDA goes idle. That is the stop signal returning to idle and waiting for the next transaction. So once we have that set up, there's typically the way that these devices work is we always have to send an address to the receiving device first. So we will start with a start bit, our start bit here. Then we'll send 7 bits of an address followed by a read or a write command. And on our particular microcontroller, we have to set up this byte. We have to set it up ourselves. So we would take 7 bits of an address, shift it over 1, and then set it 1 if we want to read from a slave, or leave it 0 if we want to write to a slave, right? then we should get an acknowledge. If the device exists, then the receiver, the slave, will acknowledge by pulling the data line low at this point, or if it doesn't exist, then it'll stay high, and that means that something is wrong. Nobody responded because that's the default state. Right? On the address byte, a NAC means that the device or address doesn't exist. Something went wrong and it's not there. So the address space for I2C is only about 112, and that's because there's a bunch of reserved bytes or reserved addresses, like this start byte. There's C-bus addresses, some high-speed master codes for negotiating speeds that are greater than 100 kilohertz, and then there's a 10-bit addressing mode and all kinds of other stuff. So these, you don't need to memorize these, just know that some address spaces, address values are reserved that we can't use. If you're not ready to, there's such a thing called clock stretching, and basically what happens is if the receiver is not ready to send or receive, the slave will hold the SCL value low until it's ready. It's basically saying, hey, wait, I need some time, and when so it'll pull that clock line low, and it'll say, hey, I need some wait, I need to wait for some processing to finish, or I need to get the data that you just requested, or anything like that. So don't do anything for a while. And often the hardware will detect this and not initiate a new clock until the clock line goes high. Then it'll start communicating again. So there's two. We've talked about masters and slaves, but the master write is a master transmitter slave receiver type of mode. And basically the transaction looks like this. We send a start bit, then we send the slave address with our read bit as 0. So we're writing, this is a master write. We're writing to the slave. The slave will acknowledge, hey, I'm here. Then the master can send some data. The slave acknowledges. Then the master sends some data. Then at the end, it'll either acknowledge or not acknowledge. And this is up to the protocol in the device. And it might be saying, hey, I'm done. No more data. And then the master will initiate a stop bit at that point. A master read is where it's a master receiver slave transmitter. And again, the master initiates the communication by first sending the start bit, then the slave address. And in this case, it's saying, hey, I'm going to be the receiver, so I'm going to set the read-write bit to 1, and I'm going to expect you to send some data back to me. The slave will then acknowledge. The master is still doing the clocking, so it's still initiating the clock. So often what you'll see for the very first byte here is that it's doing a dummy read. So you're going to be reading from some register and it'll be generating a clock, and we throw away that first byte because it's not in the register until after those clocks are generated. So the slave will be sending data to the master. The master then has to acknowledge, yes, I got it. Then the slave will send some more data. You read it again. Then the master, when it's done, will say, okay, I'm done. Send the no acknowledge. You let it sit, and then read, and then send a stop signal to the slave device, right? So let's look at an example. Here's a transaction between these, and the question we have is, what is the address that we're sending to? Is it a read or a write? What's the data that's being received or transferred? And did anything weird happen during this phase? So what I'd like you to do is to pause the video here and then take a second and try to process it for yourself. Okay, so let's look at what has actually happened here. And the first thing we want to do is we want to highlight all the rising edges. We really don't care about the falling edges. We just want to highlight all the rising edges, right? So let's do that. We've got all of our rising edges highlighted here. And the first thing we notice is that we get our normal start bit signal here at the very beginning. And then we can start looking for, on each of the rising edges, what data is being latched in. So the first thing we see is we've got a 1 on the rising edge, then we get a 0, then we get a 1, then another 1, then a 0, get another 0, get another 1, 0, 0, right? Okay, so that's our first 1, 2, 3, 4, 5, 6, 7, 8, 9 bits. So this is our address. Our 7 bits of address is so our address here is 1 0 1 1 0 0 1, right? Because it's 7 bits. These first 7 bits are the address. Then this is the read write bit, and because it's 0, that means that we are doing a write to the slave. So this is a write to address 1 0 1 1 0 0 1, right? And then the slave has acknowledged here, that's what this guy is, it's pulled the master, let it go, the slave pulled it low to say, yes, I'm ready, go ahead, let's do this, right? But what we see next is the clock line has gone low. So this is saying, yes, I'm here, then the slave is saying, hold on, let me get ready by pulling the clock line low. Right, so we have a clock stretch here, and once that's set up, then we can start latching in new data. So now this is the master, again, sending data to the slave. So we latch in a 1, another 1, another 1, 0, 0, another 1, a 0, and then we have our stop signal at the very end, right? So here, this is these 8 bits are the data that we've transferred, and what this is a combination here. It's a combination NAC. So this first little edge here is a not acknowledge, because it left it, the master left it high, and the slave said, I'm done. It didn't pull it low, so that's a NAC in this case. And then the clock also went high, so that was a stop, right? So we have an end of transaction here. You might also see in some devices, the slave will just keep acknowledging and say, yep, keep going, but the master can stop at any time as long as it initiates a stop signal this way. So you might see this go low for this very last rising edge rather than staying high like it did. Right. So the transaction here, what happened was we got an address 10110001. It's a write because of this this 0 bit here. It was acknowledged, no problem. The slave stretched the clock, and then the master sent the data, sent this data byte to the slave, which was then NAC'd, which maybe is not a problem. It just means that's the end of the expected message, and then we got a stop signal. So that's what happened during this data transfer.